Hello everyone. So today we are conducting our 7th lab, which is entitled Induction Simulation Lab, and that's my favorite lab. Okay, and I will tell you why. Well, the reason it's my favorite lab is that it has to do with Faraday's law. Well, Faraday's law is the principle behind the operation of the motor, the generator, and the dynamo. Michael Faraday discovered these devices around the year 1832. And I think it is not an exaggeration to say that the motor, the generator, and the dynamo are the foundation of modern technology. Indeed, they constitute the main devices in the operation of most power generation methods, including hydroelectric power generation, wind energy, nuclear power, coal, thermal power generation, waves, tidal power generation, geothermal, and so on. So the motor, the generator, and the dynamo also constitute the main devices in the operation of the microphone, the telephone, the radio, television, all of telecommunication, whether analog or digital, voice recording methods, including magnetic tapes, compact discs, and so on. They appear also in electric trains, fans, and many more applications. So that's basically the reason why it's my favorite lab. Alright, so we start with the first part, which has to do with the bar magnet tab. Well, here it seems we're not going to do much. You are just going to answer the questions based on the theory that you already know or that you learned in the lectures. Now, let's switch from the bar magnet tab to the pickup coil tab. Okay, I'm already on the pickup coil tab, and let's try to answer some of the questions. Okay. So I have the voltmeter, which is measuring the voltage in the coil. Okay. And when the magnet is not moving, what does the voltmeter indicate? Well, it's pretty clear here. Okay. So you'll have to answer that question. Now, if I move it around, if I move the magnet around, what happens? Is there any change in the voltmeter? Okay. So there seems to be a change. I see some change. Okay. So, alright. So if I move it across the coil, what happens? Maybe I can put the coil in the middle of the screen, and everything will be a little bit clearer. So let me move the magnet across, so from left to right. Okay, I see something. I see a change in the voltmeter. Then, okay. And if we move it from right to left, what happens? So a change. So you have to describe what you see. To help you, I can say that it all has to do with Faraday's law of electromagnetic induction. Okay, so look for Faraday's law. Okay, and look for in your explanation, talk about the magnetic flux and the electromotive force, okay, that's created by a change in the magnetic flux, okay. And you remember what magnetic flux is, right? It has to do with the magnetic field and an area, okay, product of magnetic field and area. So use that in your explanation. So now we have to increase the number of loops. There are 2 loops here, so let me increase them to 3. Okay, so we have 3 turns of the coil, and then increase the strength of the magnetic field to 100%, not 100, and the area of each turn, make it larger, 50 to 100. Okay, increase it to 100. So what happens as we move the magnet through the coil of wire again? Okay, so it's a little bit hard to do. I'm trying. Okay, I just moved it, and move it from left to right, and I just moved it again, now from right to left. So you have to be a little bit patient with this simulation. It's not that easy to move the magnet. Okay, left to right, and then from right to left. And as I do that, you can see that there is a change in the voltmeter. So you have to describe what you see. Alright, so now we can move on and go to the 3rd tab, which is the electromagnet tab. Okay, this is the electromagnet tab. So of course, an electromagnet, what is an electromagnet? It's just a coil of wire with a current flowing in it. Okay, if there's no current, of course you don't have an electromagnet if there's no current, because it's not gonna create a magnetic field. Okay, to be an electromagnet, it has to create a magnetic field, so there has to be a current flowing through the coil, and that's what an electromagnet is. Basically what it is, it's an artificial magnet. Okay, a magnet created by men, or it doesn't have to be, but where there's a current flowing through a coil. That's what an electromagnet is. We call it an electromagnet because the its magnetic field lines are the same as those of an ordinary natural magnet. Okay, so it basically plays the same role as a magnet, but I'm pretty sure you already know that. So now we can change the current source from DC to AC. So here I have an AC current, so I use a battery now. Now I have a DC current. So here I have a DC current because I have the current is flowing in just one direction. Okay. Now if I change from DC to AC, what happens to the compass? Okay, so you'll have to describe that. Well, that's really all I can say for the 3rd tab, the electromagnet tab. Now let's move on to the transformer tab. Let's see what we can learn from it. Okay, notice that there are 2 coils now. Okay, there is a primary coil, okay, the one that has a current flowing, okay, in the coil. I'm calling it the primary coil, and then there's a secondary coil. Okay, you can see the electrons, but the electrons are not moving, so there's no current there. Okay, so there's primary coil, okay, the one on the left of my screen, and the secondary coil, the one on the right of my screen. Okay. All right. So now, so what happens if the primary coil remains stationary? Of course, you see that there is no current in the secondary coil, the one on the right. If the primary coil, so with a DC source, okay, with a direct current source, when there's a direct current flowing in the primary coil, it's quite clear that there will not be any current flowing in the secondary coil, okay, because no current is induced there. Okay, and to help you out, again, it all has to do with Faraday's law. Now we need to, okay, with an AC source, what happens with an AC source? Now when we change, or let me move the primary coil first, okay, and see what the change will be.